All right, friends, it's time for another lecture with Algorithm Analysis and Design. I am your host and your professor, Dr. John Boa. This lecture, we're going to be discussing dynamic programming. So let's see what we have going on here. So what is dynamic programming? So previously we saw the generalizations of different algorithmic topics, and we also talked about divide and conquer. So there are some things with divide and conquer that look good but end up being very inefficient. So that means, do we have any alternatives? That would be the next question, I guess. So that means we have to come up with an alternative, and one of these techniques, one of these paradigms, is called dynamic programming. And this is a problem-solving strategy that breaks problems into smaller overlapping subproblems, so that's one of the keys. It solves each subproblem once and then stores the result for reuse later on. So there's two major approaches. There's a bottom-up approach called tabulation, and then a top-down approach called memoization. And this is not spelled wrong. This is memoization, as in creating a memo, not memorization. It's a different idea, although there may be some etymology similarities or something, but it is memoization instead of memorization. And it comes from the word memo, meaning to take a note to yourself. So it's about keeping a record of what you've already done. All right. So what does dynamic programming require? In order for us to come up with a dynamic programming solution, an algorithm that follows this paradigm, what are the requirements? Well, we have to have overlapping subproblems. So the overlapping subproblems means that the same subproblem appears multiple times, and they have to have optimal substructure, which means optimal solutions to subproblems combine into an optimal whole. Now, both of these are required. So the overlapping subproblems, this basically means that the problem's recursive breakdown generates the same subproblems multiple times. Okay, without that overlap, storing the results gives no benefit. So you notice this, for example, with the Fibonacci situation. It is very inefficient if you use the direct divide and conquer from the definition. And other examples, I guess, would be like the knapsack and matrix chain multiplication and things that we'll look at. Optimal substructure, again, this means that the optimal solution to the whole problem, again, can be built from the optimal solution to those subproblems. And without that property, solving the subproblems optimally wouldn't guarantee the global solution would be optimal. So examples of failure would be examples we'll see in greedy algorithm examples or certain game strategy problems. So if you have only the overlapping subproblems but not optimal substructure, dynamic programming can't guarantee the right global solution. And if you only have optimal substructure but not overlapping subproblems, you might as well just use divide and conquer because that's probably more efficient, and dynamic programming would add very little, and it requires both. So these are often used with optimization problems like min-max, shortest path, etc., and they save time by avoiding redundant computation. But no matter what anyone says, the old adage, there's no such thing as a free lunch. So that means that there's some sort of trade-off. And the trade-off that we usually have is we use extra space in order to save time. That's the trade-off. Okay, let's look at our motivation here. So why dynamic programming? Well, some problems require solving the same subproblem many times. Divide and conquer actually showed us this, but we saw that we could waste time recomputing identical results. Dynamic programming stores and reuses the results, trading the space for time. It's common in, again, optimization problems like shortest path and the knapsack problems, counting problems like number of ways to do X, and string problems like edit distance. There's a payoff often. There's huge speedups from exponential often down to polynomial, or at least improved runtime or complexity, which leads to better runtimes in general. So overlapping subproblems in action. So what is ultimately an overlapping subproblem? This is a problem, or a problem rather, has overlapping subproblems if the same subproblem occurs multiple times in the problem's recursive breakdown. Dynamic programming avoids recomputing these by storing solutions. So an example is our friend the Fibonacci sequence that we've seen before. The direct mathematical definition is that it'll return 0 if n is 0, it'll return 1 if n is 1, and otherwise, if n is 2 or greater, it returns the f of n minus 1 plus f of n minus 2. Now we saw that with our recursion tree, the naive recursion that we saw with divide and conquer calls the call tree for Fibonacci of 5, for example, just in this simple example. Fib of 3 would be computed twice, fib of 2 3 times, etc. For fib of 40, we would end up with 330 million calls, and most of those are just recomputations. So that is ridiculous and avoidable. So, memoization. We talked about tabulation and memoization, briefly mentioned that those are two approaches. What does memoization do? Well, it's a top-down approach. It stores the results of expensive recursive calls in a table, which we often call a cache. Some people say cache, but that's more of a military, like weapons cache. Some people say that, but a cache is really the appropriate way to say this. On repeated inputs, we return the stored result instead of recomputing, and it works naturally with recursion. Usually uses array if the parameters are small integers, and hash map if the parameters vary in range or type. And then I gave some examples with C++ and Python. Okay, so this is just Fibonacci examples where we are storing rather this data into an array. Okay, or a list in this case. So what's tabulation? This is a bottom-up approach. We build a table of results starting from the smallest subproblems, iteratively fill the table entries using previously computed values, and in practice this is often faster, so there's no recursion overhead. But it requires careful ordering so the subproblems are solved before use. And this is, of course, the code samples of the C++ versus Python. So naive recursion versus memoization and tabulation. We have the naive recursion. We try to solve each call independently. Easy to write, but exponential time for overlapping problems, unfortunately, like our friend with Fibonacci, the Fibonacci. Memoization, top-down recursion plus cache. The pros are, it's a simple upgrade from naive recursion, and there's slight overhead for recursion and cache lookups. And then there's tabulation. This is a bottom-up table fill, very efficient in time and often space, and it requires, the con though would be that it requires identifying the build order. All right, so we start with a brute force recursion that recomputes the same work. This would be when we're moving from a solution that looks maybe obvious, like the Fibonacci, and trying to come up with a different solution that does the same thing but is more efficient, okay, or optimal, hopefully optimal. So we start with the brute force recursion that recomputes the same work, identify repeated subproblems and a clean subproblem state. We can add a cache to cut the duplicate work out. That might be a first step. And then later on you look at it and say, well, let's flip it to a bottom up. So is there a way to do this with tabulation? This is predictable and does some easy space tweaks, so we're not holding everything. And the result, often you start with an exponential algorithm originally, and then you might end up with a polynomial, or at least a more efficient algorithm. Dynamic programming can be framed as an engineering process, so we model the state, derive a recurrence, we cache or tabulate, and then optimize the memory and the time that way. We're not really making it clever, we're just removing waste. So Fibonacci. So with Fibonacci, the T of n is exponential, so it recomputes fib of k many times. That's our problem. Memoization, the time is big O of n. It's linear, and so is the space, because we have the call stack and the cache. And tabulation, kind of the same thing. So we have big O of n for the time, big O of n for the space, but the space could be big O of 1 using two variables to optimize the space. Each time through the loop, you're just reusing those two variables instead of actually holding them in a larger container that tabulation uses. So pattern generalizes. Once the sub problems are repeated, the caching helps. Fibonacci is what we would call toy-sized. The pattern scales, so grid paths, edit distance, matrix chain, knapsack. We can use it to visualize blowups versus savings. So when do we know to use memoization versus tabulation? So memoization, again, as a reminder, is top-down. This is natural when the recurrence is clear but reachable state space is sparse. It's easy to prune with constraints, only computes needed states. The con, though, again, is the recursion, depth limits, and overhead of hash map lookups. Tabulation, the bottom up, it has tight loops typically, predictable memory, and easy to vectorize or optimize. Simple to do space reductions like one-dimensional rolling, 2-pointers. The con is that we have to choose a correct fill order, so we may compute unreachable states, which could be inefficient or cause problems. Rule of thumb, though, is start top-down to validate the state recurrence, because this is easier to come from a brute force recursion to memoization. It's easier to improve it that way. And then once you have that, you look at it and say, oh, you know what? I bet you we could take advantage of tabulation. We flip it to bottom up for production speed and space. So what are the steps in a dynamic programming algorithm? The overall steps are establish the recursive property, choose memoization or tabulation, build from the smallest subproblems, and reconstructing the optimal solution. Okay, so the first step, again, establishing the recursive property. We define the problem state precisely. So, for example, the index, remaining capacity, last choice, etc. Express the problem in terms of smaller subproblems, write a recurrence relation for the solution, verify the recurrence works for all valid inputs, including smallest cases. An example for Fibonacci is we would have something like this, right? And an example for the 0-1 knapsack problem is V of IW equals the max of the I minus 1 W, or the value at I plus V at I minus 1 W minus weight. We'll see a little bit more later on knapsack. So choose memoization or tabulation is the major step 2. Again, we've talked about these, but as a reminder, memoization, top-down, works naturally with recursion, good for sparse reachable state space, only computes needed subproblems, but it has the overhead of recursion plus cache lookups. Remember, and that can be expensive. The tabulation, iterative, often more efficient in practice, predictable memory layout, can optimize the space with what we mentioned before with the rolling arrays or 1D storage, and must know correct fill order in advance. And just for some clarification, what do we mean by rolling array? So the idea is that many DP tables, dynamic programming tables, don't need all the rows in memory. They only need the current one and the previous one. So there's 2 really. So they can use kind of an inchworm technique where instead of keeping the n by m table, we just roll between the 2 rows. So you keep track of the previous, keep track of the current. And then the next round, the previous becomes the current, or rather what was the current is now the previous, and now the new current comes into play, etc., etc. So in the knapsack problem, it was the table at IW would depend on the I minus 1 W and I minus 1 W minus W sub I. So again, we'll look at that. But instead of keeping all n rows, we alternate between the 1 rows. For the 1D storage, in case that's not clear, if the recurrence only depends on previous states in the same row, we can collapse a 2D table to a single array. But you have to update the correct in the correct direction to avoid overwriting needed values. So with the Fibonacci tabulation, instead of storing that whole array, you just need to keep the last 2 numbers. Remember, because the f of n is the previous one, f of n minus 1, plus f of n minus 2. So you just need those 2 numbers. And then that kind of, again, it's kind of an inchworm technique. It can move forward. But the rule of thumb, again, as a reminder, is that we start with memoization typically to test correctness, and switch to tabulation to produce speed, to give it production level speed or space. What about the third major step in developing dynamic programming algorithms is build from smallest subproblems. So we identify the base cases and initialize them in the table or cache, fill the table in an order so dependencies are already solved. And for memoization, we would have base cases stop the recursion. And for tabulation, the loop nesting in order is what matters. An example would be the coin change problem, using tabulation, you could fill from 0 to the amount using the smallest coins first. Matrix chain multiplication, which we'll see again. There's a little bit of a chicken and the egg problem. I think I've mentioned this before. We'll mention these problems, but we haven't really gone into detail with them. But fill diagonals of the cost table with shortest chains upward. Step 4 is reconstruct the optimal solution. So many dynamic programming problems require more than just the optimal value. So maintaining additional data in order to reconstruct the actual sequence of choices, like parent pointers, direction arrays, split points, etc. Examples again, Knapsack tracks whether each item is taken. Okay, this is going to be a problem where we try to decide how many items we can fit into a knapsack that can hold a certain amount of weight. How do we optimize the amount? So if we're a thief and we're trying to, I'm teaching you how to be better thieves if you break into a jewelry store. If your knapsack can hold a certain amount of weight, how can I optimize it to hold the most expensive stuff for that amount of weight? The matrix chain would be we track the split index K. Shortest path is tracking predecessor vertices. So reconstruction is often done when backtracking a pass over the stored decisions. Okay. All right, dynamic programming versus divide and conquer. So the subproblem type with divide and conquer is that the subproblems are independent, typically. With dynamic programming, it's better to use when we have overlapping, or we get the benefit when we have overlapping subproblems. Storage, usually we don't have extra storage with divide and conquer, so that's one of its benefits. But with dynamic programming, we have to store results of some sort. Sometimes it's a table, sometimes it's a cache, sometimes it's the rolling row, or just single values for 1D information. Work reuse. Divide and conquer keeps doing the work over and over again, like we saw with Fibonacci. But with dynamic programming, we do get the benefit of having the work done already, and we could just look it up rather than try to recompute it, right? So we're trying to avoid all of that nonsense if we can. Common examples of divide and conquer are merge sort, quick sort, binary search. Dynamic programming would be the 0-1 knapsack problem, matrix chain, Floyd-Warshall algorithm. Time impact may recompute stuff with divide and conquer, in some cases many times. And then in dynamic programming, we avoid recomputation. Why divide and conquer fails on overlapping subproblems. So in divide and conquer, identical subproblems are solved independently. Okay, and we often get some really good, efficient results. That's fine when the subproblems are disjoint, sorting left versus the right half of an array, for example. Merge sort, it works very well. Quick sort, it works very well. But it fails badly when the same subproblem appears in multiple branches. So with the Fibonacci call tree that we saw earlier with the fib of 3 recomputed, and we said, for higher numbers, you end up with millions of recomputations. So with the Fibonacci we saw for divide and conquer, we have about 330 million calls, and it's exponential. With dynamic programming, with memoization or tabulation, it's about 40 calls or iterations in its linear time. Okay, problems and principles of optimization problems. What are the principles of optimality? So what is an optimization problem? You hear this term a lot, and it's one of the most important categories of problems because we're trying to make something more, we're trying to find the best solution, often with the fewest resources that we can. An optimization problem is a problem where the goal is to find the best, also called the optimal, solution according to specific criteria. We use an objective function to answer the questions, what's the goal of the solution to this problem, and how do we measure if one solution is better than another? So that's called the objective function. Examples would be maximize. We might want to maximize profit, value, or score, or minimize. Minimize the cost, minimize the time, minimize distance, right? So shortest path, how much stuff can we put in the knapsack we want to maximize the profit while minimizing the cost in terms of the weight, right? So these are often parts of optimization problems. So usually when we say optimization problem, we're talking about minimums and maximums of some sort. And they're often subject to constraints. Okay, so there's often constraint satisfaction involved, like capacity, budget, time limits. Examples of optimization problems are shortest path between two cities, right? So maximum value in a knapsack without exceeding the weight. Minimum edit distance between two strings. In other words, how do you convert one string into the other with the smallest number of changes? Many optimization problems have overlapping subproblems, so that makes them a candidate potentially for dynamic programming. So, principle of optimality, what is this? So, an optimal solution to a problem contains optimal solutions to its subproblems. I'll say it again. An optimal solution to a problem contains optimal solutions to its subproblems. That definition is based on Bellman's definition. The meaning is that if you break an optimal solution into smaller parts, each part must also be optimal. Key requirement for dynamic programming applicability. So an example would be shortest path from A to C via B would be if I want a path A, B, C is shortest overall, then A to B and B to C must themselves be the shortest for their endpoints. For example, if you go A to B to C, but the path between A and B isn't optimal, then that means the path of the overall ABC isn't optimal. It can't be, because that means there's a better path from A to B, which means that would make the overall ABC shorter as well. Okay? So when does this principle hold? It holds for problems with optimal substructure. So shortest path, like Dijkstra's algorithm or the Floyd-Warshall algorithm, matrix chain multiplication, 0-1 knapsack, longest common subsequence, which we'll see more of with the knapsack. But in the 0-1 knapsack problem, if you're taking an item, or if taking an item as part of the optimal solution, then the remaining items must form an optimal solution for the smaller capacity, right? So with that, we might pretend that the knapsack has lower capacity, and what can we fit in those lower capacities? So when does this principle of optimality fail? It fails when the subproblem optimality does not guarantee global optimality. So common causes would be constraints or interactions between subproblems that change their context, and non-additive, could be non-additive or dependent cost structures. Examples, Traveling Salesperson Problem, optimal partial tour may not be extendable to optimal full tour without reevaluation. Game strategies where, with the opponent moves, the local optimal moves may lead to poor overall results. Okay, this sometimes comes into the old adage, you can't see the forest for the trees. You're so focused on the stuff in front of you that it may actually end up being a poor strategy for the overall system. In such cases, dynamic programming may still work with modifications, but the principle doesn't hold directly. All right, classic examples. Now we're going into specific examples. Some of these will cover more deeply than others. All right, so this first example is binomial coefficients. So what's the definition of the problem with binomial coefficients? So the definition is that we want to calculate C of n comma k. So C of n and k. The number of ways to choose k items from n total items without regard to order. So as an example, the binomial coefficient C, or combinations of 5, 2, is 10, because these are the ways rather to choose 2 students from 5. The mathematical formula that we can use is C of n k equals n factorial divided by k factorial times the quantity n minus k factorial. Probably seen this at some point if you have taken a discrete structures course, which I assume you do if you're watching this, that you've done some sort of discrete structures and you've done combinatorics or counting theory. You've probably gone over combinations and permutations. So this binomial coefficient is just the mathematical notation for combinations. So why wouldn't we always just use this factorial formula here? Why can't we just do that? Well, overflow risk with large n, because calculating factorials is very expensive. Wasted computation if we need many coefficients, right? So in many problems, n and k are large, and dynamic programming is more efficient for those scenarios. Binomial coefficients are a great example, basic example, of recurrence relation leading to a dynamic programming table. We remove the redundant computation. With real-world uses, we use it in probability and statistics, subset generation, and optimization problems, and Pascal's triangle problems in coding competitions. So learning value would be that it's low barrier, but clearly shows us the optimal substructure and overlapping subproblems. So that's one of the reasons we're doing this. Why are we even learning it? So combinatorics, counting theory reasoning, is that we include a particular element, choose k-1 from n-1. Exclude it, choose k from n-1. So we end up with this right here. So we have c of n comma k instead of the factorial definition, this mathematical definition up here. Okay, the binomial coefficient definition, we have this, okay? C of n and k equals the c of n minus 1 k minus 1 plus c of n minus 1 k, okay? So it's the combination with those previous two, okay? Or the current and the previous, or the one smaller value of k. Base cases would be c of n comma 0 is 1, okay? And c of n comma n is 1. And this would be a naive solution right here. This is just directly implementing it with the recursion, but we end up with an exponential time. There's tons of repeated calls, right? Okay, so overlapping subproblems exist, so this might be a candidate for dynamic programming. C of 5-2 repeats previous calls, like C of 3-1, C of 3-1, and then you get another C of 3-1, right? So it repeats it 3 times, and C of 2-1 5 times, right? So you have C of 2-1 would be down here 5 times. This repetition is exactly what dynamic programming saves us from. Okay, here's a memoization, top down. Okay, still starting at the top, going down, still involves recursion, okay? But we are storing things, right? We're beginning to store things. So you have this, it'll return the overall array, but we're also calculating these as we go along. Tabulation, more efficient, bottom up. With this example, notice that we are avoiding doing any recursive calls, okay? What we're doing is we're looping through the elements and storing the values as needed, starting from the bottom all the way to the top, okay, as needed, and we can make use of that optimization. It's much faster that way. Here's a visualization with Pascal's triangle for n equals 5. You'll notice that n equals 0, we have 1, n equals 1, 1, 1, n equals 2, 1, 2, 1, n equals 3, 1, 3, 3, 1, right? Because each of these values is calculated this way. So showing n equals 5, on row 5, we have C of 5, 0 is just 1, right? So that's this. And C of 5, 1 is 5, okay? C of 5, 2 is 10. C of 5, 3 is 10. C of 5, 4 is 5. C of 5, 5 is 1, right? Optimal substructure. This is a key takeaway from this, is that C of n comma k from the C of n minus 1 k minus 1 plus C of n minus 1 k. That is, the problem of computing C of n comma k can be optimally solved by combining the optimal solutions to its smaller subproblems, these. There's no need to revisit or revise the subproblem answers later. So starting at the bottom going up, you can calculate these, and then when you get a further C of n minus k, you can calculate that based on previously calculated values. Overlapping subproblems exist in the binomial coefficient, because there's many repeated n comma k calls in the recursion. And dynamic programming advantage would be we can take the exponential down to a polynomial. Simple recurrence that maps perfectly to a dynamic programming table. Another example we've alluded to, and I briefly explained it, but we're going to go a little bit deeper into it. What is the 0-1 knapsack problem? So here's a real life scenario. Again, teaching you to be better thieves. A thief burglarizing a store wants to take the most valuable load that can be carried in a knapsack capable of carrying at most W pounds of loot. So given n items each of those items, okay, maybe it's a golden candlestick, a jewelry, a necklace, a ring, earrings, a diamond brooch, all these different things from this store. I'm using jewelry. It doesn't have to be jewelry, but too many spaces there. But we have a value and we definitely have a weight. So each of those things weighs something. Okay, we're not considering size, like does it fit in the dimensions of the box? That would be a different animal altogether. But for this, we're concerned with weight. Okay, so we assume based on their just physical dimensions, all of them, you could fit any number of things inside the knapsack. So we're focused on the weight and the value. So we want to maximize. We have a maximum capacity of W, and we want to maximize the total value without exceeding the capacity. Okay, so it could be right up to the capacity. It could be less than the capacity, but it cannot go higher than the capacity. So that's our constraint. Each item can be taken 0 or 1 times. This is the 0, 1 knapsack. There's no fractional item. Okay, so we can't take part of the diamond ring. That doesn't make sense. So real life scenario, a thief burglarizing the store wants to keep those most valuable load. Okay, I don't know why that's there twice. That's weird. That should not be there. All right, so the brute force approach, though, is to determine every possible pair of value weight combinations that can go into the bag. But that is exponential time. That's bad. We don't want that. So here's a simple example. So let's assume there are 3 items available and I want to maximize what I take. So these are my items sitting in the jewelry case. I've got item 1, item 2, item 3. Item 1 is worth 60 and it weighs 10 ounces, 10 pounds, 10 kilotons, whatever. Very strong knapsack. Probably made, it's Carhartt or something. Item 2, 100 value is the value and it weighs 20. And then we have item 3 is worth 120, but it was 30. So if the weight is 50, that's the top weight that we can hold. The maximum value ultimately is going to end up being 220 because we'll end up taking items 2 and 3. Now, why are we doing this, and how would we have done that? Okay, we'll get to that in a minute, but why are we doing this even? So it's a classic optimization problem, the knapsack problem. In fact, I use this nice little image over here in the slides to show a knapsack. It's widely used to teach dynamic programming on real-world constraints. It has optimal substructure. Principle of optimality is in action. Overlapping subproblems when recomputing the capacity left scenarios. Applications would be things like, now, real-world applications would not be me helping you, burglarize a jewelry store. Instead, hopefully you don't do that, because I will turn you in if the cops ask. Budget allocation, resource scheduling, and cargo loading. These all benefit from this type of problems. What all can we fit in this truck? This truck can only has so much capacity. That would involve dimensions and weight, right? So it's a little bit more advanced than this. But ultimately, that's the general idea, is we want to be able to optimize these different things. So it is involved in supply chain stuff. So recursive property for the 0, 1 knapsack is let V of I comma W equal the maximum value for the first I items with capacity W. And the recurrence looks like this. So V of I W is equal to 0 if I is 0 or W is 0, or, so if either of those is 0, V of I W is equal to V of I minus 1 W if the weight at I is greater than W. Okay. The otherwise, okay, if the weight is not, okay, so we would assume it's greater than 0. Okay, so if the weight of the item we're trying to add is greater than the remaining capacity of the knapsack under our consideration at this time, we just keep the V at I minus 1, okay, the previous item, all right, and its weight. Max, otherwise, so meaning, I started to say it, but if the weight or capacity left is greater than 0, and we're not on item 0, meaning we have items to look at. If the weight capacity is greater than 0, but the item we're about to try to add is less than or equal to the remaining capacity, then we take the maximum of that previous value, okay, the v of I minus 1, so using the previous item, and then we try the value sub I, okay, the value of the current item I plus the previous item with our capacity minus that weight sub I. So that means we might have to take out the previous item, right? So so ultimately what we're doing is we're making a choice here. So this is the choice step. Do we include the item I? Okay, so that would be that first part. That's basically ignoring the new item and keeping the old solution. I said it backwards here. So we exclude this first item, or the new item. We keep it the way it is. Or we include the item. We take the new item, so we add its value v sub I and reduce the capacity by weight sub I is what I meant. All right, so basically the max will choose the better of the two for us. All right, here's the solutions. This is the naive recursive solution for the knapsack. This is exponential time, recomputes many subproblems. So using kind of a divide and conquer technique, this is really, really inefficient. So we can improve on it with memoization. So we get big O of n times w. So we get total number of items, and then the weight capacity here, we've got time and space for both. And tabulation improves it even further, right? We're avoiding recursion and things like that. All right. So the general steps for building the DP table these are essentially the in English steps for the tabulation algorithm. So you set up the table. The rows equals the items considered 0 to n. Columns is the capacity 0 to w. DP at IW equals the maximum value using the first I, that should be a lowercase I, first I items with capacity W. Initialize the base cases. So if I is 0, meaning no items, we set DP at IW equal to 0 for all the weights. If W equals 0, capacity 0, DP at IW for all I. We'll fill the table row by row. That's step 3. We'll see that in the next slide. And then final answer would be after filling the table, DP at NW contains the maximum achievable value. Okay, so or maybe it's the slide after, I forget. But anyway, here's the general step. Fill the table row by row. We've got for each item I, 1 through n, and each capacity 1 through w. If the item doesn't fit, meaning the weight of that item greater than w, then we copy the value from the row above. Okay, and then we skip the item if it's too heavy. We don't add it. If the item fits, meaning the weight of the item is less than or equal to w, we compute both options. So we compute what it costs to skip the item and what it would cost to take the item. So can we take the item? And then we take the maximum of those two. So if it will fit, what's the better thing to do? Do we skip it or do we take it? So here's a worked example. So let's start with our 3 items from earlier. We have values 60, weights 2. I think I'm using different numbers for this, so it's similar to the one earlier, but not the same. So reiterating, the item 1 value 60, weight is 2. Item 2, value 100, weight is 3. Item 3, value 120, weight is 4. And the capacity of our knapsack is 5. That's the weight capacity. So state DP at IW is the best value using the first I items with capacity W. The transition is if the weight at I is greater than W, then we set DP at IW for the item at that weight equal to the previous one, previous item W. In other words, we can't take it, so we copy the value from above. In other words, leave it alone. Otherwise, if this is not the case, if the weight is not greater than the capacity remaining, we find that max. Okay, that means skip versus take. We have to choose. Okay, so we have DP at 0, W is 0 for all the W's, and then DP at I0 is 0 for all the I's. So we end up with the weight, if we consider at 0 weight, we have 0 there. We have 0 for 1, 2, 3, 4, and 5, all the way up to that maximum. Okay, that's how we initialize it. So what are we doing? So we're processing item 1. Value is 60, weight is 2. We saw that earlier. So for capacities less than 2, these are the ones we are assuming. If the capacity, okay, if we assume the capacity is less than 2, like these two, then the item doesn't fit. So we just copy the value from the row above, which is what we do. So this was the initializer row right here, right? But what do we do? I'm just going to move it up there for a minute. Let's see here. Is this going to be better? Let's see if we can get this a little bit nicer. There you go. Okay. Oops. All right, there we go. Live television. So we have the, I'm going to move that. So the table's right here. We have a little bit more room now. There we go. So this is our initialized row. But what do we do for considering this item, this first item, item 1? The capacity, if we assume our knapsack has a 0 capacity, we can't take it. If it has a 1 capacity, we can't take it. If it has a 2 capacity, 3 capacity, 4 capacity, or 5 capacity, then this thing with weight 2, we can take it. Okay, and that improves it because we had 0 before, and now we have 60. That's the value. Okay, 60 plus the value from the row above at reduced capacity is what we do with taking the item. So we take the item for all of these instances, right? So with the 0 and 1, we can't take it, so those stay 0. And then for w equals 2, if we're considering the capacity available is 2, we take the max of 0, which is the thing above it, and then take the value of 60 plus the thing above it. So keeping the, quote, thing above it in the knapsack, but also adding this new thing. There wasn't anything before, so that's why we're adding dp at 0, 0 is just 0. We're just adding our 60 here, and our 60 is bigger, so we take that. So we take this item in all of these instances. Processing item 2, this is the thing with value 100 and weight equal to 3. For capacities less than 3, the item won't fit. Since it's a weight of 3, we assume this new item will not fit, so we don't take it for anything less than 3. Okay, so 3 occurs up here. But for capacities greater than or equal to 3, we compare, do we skip or take? So for w equals 0, we just copy the 0 above it, copy the 1 above it. For w equals 2, we can't even consider taking this new item, item 2, because the capacity, if we have a capacity of 2, we can't fit it. But we copy the value above it, 60, not 0, right? Because we already have that item 1 inside there. With w equals 3, what happens here? So we take the max of skipping taking the new item. In that case, we would keep the 60, okay? Otherwise, we take the item. So it's 100 plus the 1 and 0, okay? 1, 0 value. And that yields 100, okay? So when we're deciding whether to skip or take, with the take, why is it 100 plus what? Where did the DP10 come from? Why are we looking at this and not the one above it? Because remember, it's not looking directly above the item with that weight. It's basically considering if we reduce the weight by that much, what can we fit in here? So what we do is you look above, okay, and then over 1, 2, 3, because that's how much this weighs is 3. So that's why we're getting a 0, because it's DP at 1, 0. For the other one, if I have a weight capacity of 4, I have to decide to keep the 60 from before, or to try to fit it in here by adding the new item plus what was in the bag minus my weight. So what's my weight? 3. So I go 1, 2, 3, and I end up in this cell. That's DP at 1, 1. And then what do I do with weight of 5? If I have weight of 5, I again look up and then over 3, 1, 2, 3. So since my weight is 5, I can keep the old item, which weighed 2, and still include this new item, which weighs 3, and I get both. So I get 100 plus DP of 1 at 2, or 1 and 2, which is 60. So it's 100 plus 60, and that's 160. That's the max, so I take both. So here is our item 3 that we're going to try to process now. So since this one has weight of 4, we basically just copy from 0 to 3, right, from above. So we ended up with these items copied down to this. Okay. Now what about the next one? The next one, weight equals 4. So we can skip, and that means 100. We would take the item above. Okay. Or take means we take the value 120 and add d at 2 of 0, which is the capacity. So that's 4 over. So 1, 2, 3, 4. So 2, 0 gives us 0. So that means we'd have to essentially think of it as emptying the sack of whatever else is in there and taking this new item, which gives us the maximum 120. Now, what about w equals 5? So for this one, we can skip and or take it, and we end up taking it because this gives us 160 ultimately. This isn't right. Sorry, this is a mistake. This should be skip with 160, and then that should be 120. Yeah, okay. There we go. That's better. I don't know how that ended up that way, but anyway, that's skip is 160 because that is the value we already have in the bag, or we can take this new item with weight 4 with the 5 by taking our 120, adding it to d at 2 of 1 because we need that 4 capacity. So we go up 1, 2, 3, 4. We get 0 over here, so we have nothing in there, no value. So we could just remove the last 2 items and then add this item and get 120, or skip taking this item and keep the other 2 and keep 160. So the skip wins. All right. All right. Now, so the final answer ends up being in I equals 3, W equals 5. That is our 160. And we got there by taking items 1 and 2. So we did not include item 3. We removed that. Okay. So actually this should say summary and final solution. All right, that was probably a copy-paste issue. So max value is dp at 3 and 5. That gives us the 160 from the previous 2 items. All right, now, what are some graph problems that are available with dynamic programming? Okay, so why does dynamic programming fit graphs in a lot of cases? So the reason is that many graph problems have overlapping subpaths, which are overlapping subproblems, right? So optimal substructure, we have the shortest subpaths forming the shortest overall path. Common dynamic programming in graph scenarios would be things like shortest path, reachability and connectivity, and counting paths. Core idea would be store intermediate results to avoid recomputation, even across different source target pairs. The difference between, or differences from a breadth first search and Dijkstra would be that dynamic programming can handle negative edge weights or all pairs shortest paths in a unified way. Okay, so when do we use dynamic programming? When we have multiple queries, many source-destination pairs, the graph is dense, which means it has many edges. Negative edge weight exists, but no negative cycles. When we would use search, like breadth first search and Dijkstra's algorithm, when only one source or few queries exist, the graph is sparse, few edges relative to the vertices, or all edge weights are non-negative. Dynamic programming often trades extra computation up front for fast, repeated queries. Bellman-Ford algorithm is our next look here. So the purpose would be to find shortest paths from a single source to all vertices. Okay. Key features works with negative weight edges, negative weight edges, but no negative weight cycles. The dynamic programming perspective would be that the state of the DP at KV is the shortest distance to vertex V using less than or equal to K edges. So it's kind of a similar idea to what we did with the knapsack, except we're now going with number of edges or edge weights and things like that. Okay. Recurrence looks like this. So it's an optimization problem, right? We're finding a minimum here. dp at kv equals the minimum of the dp at the k minus 1 v and the dp at k minus 1 u, plus w, the weight, at u comma v. So adding that extra, the weight of that new edge. Complexity would be the big O of VE time, slower than Dijkstra, but more general. Applications, routing with penalties, currency arbitrage detection. Distance vector routing uses Bellman-Ford. Okay, so that's if you're coming from a network background or you're interested in networking algorithms, distance vector routing uses the Bellman-Ford algorithm. Basic example, initialize all distances to infinity except for distance of source equal to 0. Repeat v minus 1 times. For each edge, u and v, update the distance at the vertex to the minimum of the distance at the vertex, which is the current distance, comparing it to the distance of the u plus wuv. If a further update is possible after v minus 1 iterations, a negative cycle exists, so that would be bad. How is this related to dynamic programming? For iteration, each iteration expands the set of allowed intermediate vertices and edges, just like the Floyd-Warshall, more on that momentarily, from a single source, though. So before going on, we want to know, what is transitive? Because we're going to use this term. So what do we mean by transitive? In preparation for the upcoming topics, let's review it. In graph theory and relation theory, a relation R, okay, that's something relating items. So in this case, two items, A and B. A relation R is transitive if those two things are in the relation and you have, if you have A and B in the relation and B and C in the relation, then that means A and C also have to be in the relation, okay? In plain language, if you can go from A to B and from B to C, then you can go from A to C, okay? This is the graph-related explanation, right? In a directed graph, transitive means that if there's a path from A to B and one from B to C, then there has to be a path from A to C, even if there's no direct edge, because we could go first to A, or first to B from A, and then from B to C. So ultimately you can get there. Another term you need to know for the next set of slides is a closure. What is a closure? A closure of a relation is the smallest relation that contains the original relation and satisfies a certain property. For example, reflexive closure means that we add edges so that every vertex has an edge to itself, so it's reflective on itself, like a mirror image, your reflection. And symmetric closure means we add edges so every edge has a reverse edge, okay? So if we're going from A to B, we also go from B to A. And a transitive closure means we add edges so the relation becomes transitive, right? So that was kind of our previous thing. So A to B, B to C, then we add an edge from A to C. So we have a direct. Smallest in this case, smallest relation, means we don't add anything unnecessary, just enough to enforce this property. So what is a transitive closure? So when we combine these two concepts, the transitive closure of a directed graph or relation is the graph you get after adding the minimum number of edges so that the graph is transitive. This means if there's a path from U to V, possibly through other vertices, the transitive closure has a direct edge U to V. So if I go from U to C to V, then I also have a direct edge from U to V. You're essentially pre-computing reachability. Before closure, you might have to follow a chain of edges to see if U can reach V. But after you perform the closure, transitive closure, there is a single edge for every reachable pair from the origin. Okay, so this is kind of ugly. I wonder if I can make that a little bit better. Increase the line spacing a bit, maybe. No, didn't really help. Let's see here. I'm going to mess with this a little bit. There we go. That's a little better. Okay. So, Warshall's transitive closure. What's the purpose? We determine reachability for all vertex pairs. Is there a path from I to J? That's our question. Okay, all vertex pairs, not just one. The input would be an adjacency matrix, where 1 means an edge exists, 0 means no edges exist. The dynamic programming perspective is that the state, so we have reachable, reachable at Kij is equal to true, if there is a path from I to j using the intermediate vertices, any intermediate vertices from 1 through k. Okay, so the recurrence looks like this. Reachable at kij equals the reachable at k minus 1 ij, or reachable at k minus 1 ik, and reachable at k minus 1 kj. The complexity of Warshall's transitive closure, we have big O of v cubed, so the number of vertices is really what our n equals, so we would say it's a quadratic algorithm with respect to the number of vertices, v. Okay, that's our problem size. And it has v squared space. Applications, compiler optimization, database query planning, and network connectivity analysis. So how does this algorithm work? We start with an adjacency matrix that I mentioned before, direct reachability. So for k equals 1 to v, we consider whether our vertex k can be used as an intermediate point between I and j. If both I leads to k and k leads to j, that's our reachability, then I to j becomes reachable, right? That's our transitive closure. By the end, reachable at ij is true if any sequence of edges connects I to j. So a pattern alert, the triple nesting structure is identical to the Floyd-Warshall algorithm, okay, that we'll see, but with Booleans instead of distances. All right, here's our Floyd-Warshall algorithm. So we know a little bit about the closure. What do we do here? So what is Floyd-Warshall, or why are we studying it? So the goal is find the shortest paths between all pairs of vertices. Why not just run Dijkstra's algorithm from every vertex? Well, works for non-negative weights, but runs slower on dense graphs with many edges. And Floyd-Warshall handles negative weights, but no negative cycles in a single uniform process. It's more general, and it gives you the overall graph shortest path between all pairs of vertices. Key strengths are that it has a simple triple loop implementation, works well for dense graphs, and big O of vertices number cubed is fine when the number of edges is approximately v squared as far as density is concerned. So produces both distances and the path reconstruction info. So it's very, very good for that. It uses dynamic programming. Okay, so shortest distance from I to j uses the intermediate vertices from the set 1 through k. Build up from k equals 0, only direct edges. 2k equals v, any vertex allowed as an intermediary or an intermediate. I'm giving you the recurrence again. I gave it to you, I think, earlier. When considering vertex k as an intermediate, we either get the shortest path from I to j does not go through k, so we keep the current distance. So that's similar to don't put the new item in the knapsack, right? Or the shortest path from I to j goes through k. So then we would try I to k to j. Okay, put the item in the knapsack. So it's a very similar idea. How do we apply it? Well, the setup is we create a distance matrix, so dist matrix. Distance ij equals the weight at ij if an edge exists. It equals 0 if a vertex to itself is distance 0. And then if no edge exists between I and j that we know of, then we put infinity. Okay, and we allow intermediates. Okay, so for each k in 1 through v, for each I in 1 through v, and then for each j in 1 through v, that's our triple loop here, we find this minimum at each step. The result is that after all the k are processed, the distance ij contains the shortest distance from I to j. Optionally, we track a next matrix to reconstruct the paths, so a little bit more memory to reconstruct it. So here's a step-by-step example with Floyd-Warshall. Here's our initial distance matrix. We see that A is connected to C and B without going edges. So A is connected to C and B. It has a 0 with itself. That's why this diagonal here is 0 for each of these, because each of these has a distance of 0 from themselves. A to B is 3. That's why we have a 3 there. A to C is 10. That's why we have a 10 there. A is not directly connected to D with an outgoing edge, because this is a directed graph. So the A to D is set to infinity, whereas D to A is 7, because it's directed, right? D can get to A. But we're not aware of how to get to D from A, or we don't know if we even can. All right, so that's our distance matrix. The first iteration would be setting K equal to A, okay? In other words, we use A as the intermediary. The update rule would be try to improve paths via A. We'll use D instead of dist for brevity, but it's the distance calculation. So we want to essentially check all pairs ij with k equal to A. So compare A to A. If you compare the distance A to A with A to A plus A to A, you still end up with 0, so that's no change. For AB, compare D, the distance AB, with D of AA plus D of AB, same as current, so that's no change. AC has no change, AD has no change, so row A will actually stay unchanged. Now, check pairs with J equal to A, column A. Okay, that's our next step. So we look at column A. We do BA, compare D of BA with D of BA plus D of AA, there's no change. C of A, no change. D of A, no change. Column A stays unchanged. So now we can focus in on the, quote, real checks, where both I and J, meaning neither the row nor the column, are A themselves, okay? But we will go through A using, starting from B or C or D. So BC, if I want to go from B to C, I compare D at BC, okay, to D at BA plus D at AC. Since D of BA is infinity, no change, because there's no improvement by going through A. If I try to go through A using C, starting with C, as far as C is aware, it's connected to A with infinity, so that's not going to help. B of D, we compare D of BD to D of BA plus D of AD. And since B of A is infinity, no change. Same thing for CB. C of A is infinity. Same thing here. AD is infinity, no change. Okay, what about D of DB? So compare D of DB to D of DA plus D of AB. Neither D of the distance of DA or the distance at AB is infinity. Okay, so DA is 7. And then we have the AB is 3. Neither of those is infinity, so let's see. So our current DB, as far as we're concerned, DB was infinity. That was our previous value, right? DB is infinity, because we did not have a direct edge from D to B. So can we update it? And the answer is yes. Actually, you can if you go from we get D of A, distance of DA plus distance of AB, we end up with 7 plus 3. So what this is saying is we can go through A from D to A to B, okay? And that gives us a path from D to B, as if we had our own little edge that was 7 plus 3, or 10, okay? So that's why we update it to 10, because that's better than infinity, for sure. Same thing with DC, we do get another improvement here. DC is currently infinity, okay, because there's no connection between D and C directly, no edge. So we consider we consider the distance of DA. So going D to A is 7, and then from A to C is 10, and that's 17. And that's way better than infinity, so we update that to 17. Now, you would then pick k equals b and then run it through the vertices again. I'm not going to do the whole thing, but I showed you the step-by-step on A. But you would do it for B, then you do the same for k equals C, then k equals D. At each step, you'd be improving the table, and you'd end up eventually getting this final table right here with all the minimum distances. Awesome. Okay, there's some C++ code, very small, not going to go over it. Other notable dynamic programming problems. So what do we have here? A problem for matrix chain multiplication. Given a sequence of matrices, find the most efficient way to parenthesize them to minimize the total number of scalar multiplications. Why dynamic programming? Different parenthesizations lead to different costs. Subchains overlap. So recurrence is the matrix multiplication of ij is minimum of m of ik plus m of k plus 1 j plus the p sub I minus 1, pk, pj, where the p are the dimensions. Okay, so what does this mean really in a practical example? If we want to multiply matrices A, B, and C, we have A of size 10 by 30, B is size 30 by 5, C is size 5 by 60. So we can multiply them. But does it matter if we multiply A by B first or B by C first? Obviously, A by C is not an option because they don't have the same inner dimensions. 5 and 30 don't match. But can we group it with AB or do we group it with BC? So this observation, because of associativity, the quantity AB then times C is the same as A times the quantity B times C. So the result will be the same matrix, but the number of operations can differ drastically. The cost of parenthesizations are A quantity AB times C versus A times quantity B times C. So with AB, you multiply the A, the 10 by 30, with the B, which is 30 by 5. You end up with 10 by 30 by 5, or 1,500 multiplications, with the resulting matrix of 10 by 5. So that's 1,500 matrices, or 1,500 multiplications. Number of additions. Well, yeah, I guess it would be multiplication. So multiplications are operations with each, right? So now we multiply the result, AB, size 10 by 5 by C, which is 5 by 60. So that's 10 by 5 by 60, and that's 3,000. So in total, we did 1,500 to get our AB. And then when we took that resultant matrix, we multiply that by C, that's another 3,000. So adding that number of multiplications together is 3,000 plus 1,500, that's 4,500. Okay. Now, what if you do it the other way? What if we do BC first? So if I multiply B, which is 30 by 5, by C, which is 5 by 60, we get 30 by 5 by 60. That's 9,000 multiplications. Already, I could just say, throw it out, don't need it. Because that's bigger than our total. We haven't even gotten to the part where we try to multiply it by the A in the front. But we'll do that just for the sake of seeing the difference here. But it's already double the size, so we wouldn't need to go any further, really. Resulting matrix is 30 by 60. Now, what about our A? Our A is a 10 by 30. So 10 by 30 by 60 is 18,000. So in total, though, we have the 9,000 plus 18,000. That's 27,000 multiplications versus 4,500 multiplications, 4,500. So clearly, multiplying AB first and then multiplying by C is more efficient. Okay, that's the chain multiplication problem. Why could this be solved using dynamic programming? For 3 matrices, we could manually check both options, but for n matrices, matrices, I don't like that at all. Here we go. Not matrices, that's even worse. Matrices. For n matrices, there are exponentially many ways to parenthesize, okay? The key is that each subchain, like A, B, or BC, appears in multiple parenthesization, so recomputation would happen if we use pure recursion. Dynamic programming saves us by storing the cost of each subchain and reusing it. So the exponential blowup of possibilities is transformed into a manageable, although not in all circumstances not necessarily super efficient feeling, but definitely more manageable, going from exponential to cubic, so big O of n cubed, by solving these overlapping subproblems. So overlapping subproblems are the cost of multiplying the subchains, and we use optimal substructure. The optimal way to multiply the whole chain depends on the optimal way to multiply subchains. Okay, we only saw one with 3 matrices, but we could have a dozen, we could have 2 dozen, we could have 100 different matrices we're trying to multiply. Another problem is the traveling salesman problem. Find the shortest route, visiting all cities exactly once and returning to the start. Why dynamic programming? Well, brute force tries n factorial number of tours. Dynamic programming reduces this to big O of n squared 2 to the n. Now, that is not great. It is definitely not polynomial, but it's also not factorial. So, strangely enough, a quadratic multiplied by an exponential is actually better than doing factorial number of tours. That uses what's called the Held-Karp algorithm. It's still not great, but it's way better than factorial. Definitely not polynomial, though. Okay, so recurrence subset, dp, is this right here. Minimum of the dp at s minus j, the set not considering j, comma I, plus d at ij. So S is the set of cities that must be visited. J is the last city in the subset, the one we end at. So S minus j is just saying the set without the city j. You might also see syntax like this. So backslash j, that also means minus. Okay, so that's just another syntax for the same thing. All right, so the set S without the city j. So an example would be if I have S is 1, 2, 3, 4 integers or cities, or pens with cows in them, it doesn't matter. 1, 2, 3, 4, and then j equals 3. Then S minus j would be you take out the 3, so you end up with 1, 2, 4. So recurrence ultimately says what? So this looks a little complicated. To get the best cost of visiting all cities in S and ending at j, okay, in S ending at j, you must have come from city I in S other than j. Okay, that's what this says down here. After visiting all cities in S minus j. Okay, before the example, let's get the fundamental meanings down. Again, dp at sj is the minimum cost to start at fixed start city, visit all cities in S, and end at city j. So dp at, as an example, dp at the set 1, 2, comma 2 means the cheapest cost to start at city 1, visiting the cities 1 and 2, and ending at city 2. Another example, if I have dp of set 1, 2, 3, comma 3, means minimum cost to start at city 1. We're always starting at city 1. That's implicit to what our discussion is for this particular set. It's not visible in this right here. This is just saying we want to visit cities 1, 2, 3 and end at 3. But we're implicitly saying, hey, let's start at city 1. Our start city is never formally specified in the recurrence, but we declare it before we start the calculations. So here's a very tiny example of a TSP, Traveling Salesperson Problem, with 4 cities using the held carp DP recurrence. So suppose city 1 is the fixed start city. So we're supposing that from the beginning. And of course, the distances are given in the table. Okay, so obviously we don't consider distance from the city to itself, but 1 to 2 is 10. You can see this is actually a mirror image across the diagonal, right? Because from city 4 to 3 is the same from city 3 to 4, right? That makes sense. Now, base case, the DP of 1, okay, traveling to city 1, traveling to city 1 and having visited only city 1 with a starting city of 1, that costs nothing. Now, subsets of size 2, we have start plus one other city. So 1, 2 with 2. And as we discussed before, we end at the city that is this second parameter type thing. Oh, you know what? That should be a square bracket now that I look at it. Okay. So that's the end city. So visiting cities 1 and 2, ending at 2. So we take the dp of 1, 0 plus dp of 1, 2, okay, equals 0 plus 10, that's 10. So the S, the set equals 1, 2, and the J, our end, is 2, and our starting city, we assume, is 1. Okay, that was given as the fixed start city through this entire exercise. Now, dp of 1, 3, 3 is 0 plus 15, that's 15. dp of 1, 4, visiting cities 1 and 4, 4 is 0 plus 20, that's 20. Okay, what about subsets of size 3? Let's keep going. Going through cities 1, 2, and 3, and ending at 3, starting at 1, ending at 3, we find the minimum of the dp of 1, 2, ending at 2, the distance at 2, 3, and the dp of the 1, 1 plus d at 1, 3. So that gives us the 10 plus 35 and 0 plus 15. You know what? I think that's supposed to be a plus, right? Yeah. Okay, so we have the d at 2, 3 is our 35, right? 2, 3. and the minimum that ends up being the minimum of 10 plus 35 and 0 plus 15. So it's 45 and 15, the minimum's 15. What about subset of all 4 cities? So in this case, we have the min of the 1, 2, 3, 3 plus 3, 4, 1, 2, 2 plus 2, 4, and then the 1, 3, 3 plus 3, 4. We end up with the minimum of 15 plus 30, or 10 plus 25, or 15 plus 30. So we end up with 45, 35, 45. So we end up with 35 as this answer. Okay, so that's our final answer. Return to city 1, or I'm sorry, you have to return. So return to city 1, we find that minimum, ending back, plugging in the previous values, end at 2, end at 3, or end at 4. And then this gives us our result, right? We get the 55, 80, or 75. Complexity and trade-offs. We should do this briefly for basically calling it a day on this. So time complexity of dynamic programming solutions. Dynamic programming often reduces exponential recursion to polynomial time, not always. But Traveling Salesman Problem, for example, goes from n factorial brute force down to quadratic exponential, which is still bad, but it's better. Okay, so matrix chain multiplication goes down from exponential, naive recursion down to cubic with dynamic programming. Space complexity considerations. Well, the standard dynamic programming uses tables. So these are tables with sizes proportional to the subproblem count, and it can be significant. So matrix chain multiplication uses big O of n squared, or quadratic space. The traveling salesman problem uses n times 2 to the n space. Okay, and then space can limit feasibility as much as time, so we have to be careful with that. When do we use dynamic programming? Overlapping subproblems. Same subproblem solved repeatedly. Optimal substructure, mentioned before. We'll mention it again in the summary, I'm sure. Optimal solution can be built from the optimal subsolutions. And if neither property exists or either property doesn't exist, dynamic programming is not the right tool. For space optimization, we store only what's needed. Many dynamic programming recurrences only depend on the previous row or column. That's what that rolling array type thing we were talking about. So that can reduce from basically a matrix or a 2D array down to linear, like keeping track of a row, right? So that's much more significant, a very significant savings. Example would be Fibonacci store 2 numbers instead of an array. So you're going down from, in that case, you're going down from linear to constant, okay? Always 2 numbers, no matter how large the array is. Trade-off would be less memory versus more recomputation if you're not careful. All right, so summary, again, dynamic programming solves problems by breaking them into smaller overlapping subproblems and storing results to avoid recomputation. Key requirements, you need to know these. Key requirements, overlapping subproblems and optimal substructure. Okay, overlapping subproblems, optimal substructure. Efficiency gains often transforms exponential brute force algorithms into polynomial time, or at least better than current, like the TSP solutions. Trade-off usually uses extra space to save time. Pretty much always uses extra space. Depends on how much extra space, right? So you could use a couple different values or entire tables or large caches or something. When do we use it? Optimization or counting problems are common. Subproblems repeat and combine into optimal whole. The optimization techniques that we talked about were memoization, which is top-down. That's a good, sometimes it's the best we can do in some cases, but often you're able to go back from bottom up after you've gone from a brute force to a memoization. You might notice that you can do a tabulation version, which will save you even more time and space in many cases. Space optimization, store only the last needed row, column, or values that you need instead of an entire array or matrix. The bottom line is that dynamic programming is not about making problems clever. It's about eliminating waste by reusing our work that we've already done. All right, so that's what I've got for you for this bit of information. So if you have any questions, please let me know. Talk to you later. Bye-bye.